So today we will continue the series of lectures on the system of thin pipes. So we are addressing of course, the micropolar case. And first we will talk a bit about the problem settings. So this will be the paper that I will be following by Beneš and Pažanin from 2016, I think. I will separate this lecture in two parts because there are some differences with regards to the Newtonian case, then I would like to talk a bit more about this. So the paper that we are following is Beneš and Pažanin. So it's from Acta Applicanda Matematička 2016. Okay, it's on Google Drive, of course. So the domain is basically, of course, the same as in the previous lecture. So same domain. As in 4.1. So you have the omega epsilon domain, which includes the junction, which is of order epsilon, and the thin pipes, which are, we have m thin pipes. So you have a big union from 0 to m, omega epsilon I. Okay, I will not repeat all the notation. You have it from last lecture. So the flow is described by the micropolar system equations. We mentioned it a couple of times, but I will write it down again. So the flow is described by the micropolar system of equations. So we have the following system. We'll basically, again, look at the linearized system, but I will write it in full nonlinear form here. So and basically, the nonlinear term does not add almost anything into it doesn't add anything into the first two terms of the expansion, only if you want to look at the general form or the second order corrector or above. It's just, you just need to address it in the error estimates. But it is more or less standard with some Sobolev estimates, etc. So there's not too much exciting regarding this here. So u epsilon times u epsilon plus gradient p epsilon is 2 dr rotation of v epsilon so divergence of u epsilon is 0, and the angular momentum equation is minus ca plus cd Laplace v epsilon minus c0 plus cd minus ca gradient divergence v epsilon plus the nonlinear term plus 4 near v epsilon is 2 near rotation of v epsilon. Okay, you saw this system a couple of times. I addressed it in the regular thin pipe. I think also, I'm not sure if we did it for the curved pipe, but again, this is the last time, at least in my series of lectures, that we will be talking about it. The boundary conditions are more or less classical. So boundary We are always trying to model problems with boundary conditions that, at least in some sense, can be regarded as physical. So U epsilon is 0 on the lateral boundary. U epsilon cross product by E1 is 0 on the exterior ends. And of course you have the given pressures. So on the exterior ends, sigma epsilon I, where I is 1 to m. And the unphysical condition, but it's, at least in this 2016, from the mathematical point of view, this is what was mostly considered. So on the micro rotation is 0 on the whole boundary. Basically, the physical boundary conditions, where you have either the dynamic boundary conditions or that micro rotation is in some sense dependent on the, for example, rotation of U epsilon. They were considered a long time ago, from the 60s, in the engineering literature, but not much has been done regarding the well-posedness from the mathematical point of view. Recently, there have been some results, and with Professor Benesh, we also did, as I mentioned before, some results. So I want to emphasize this again. So there are other generalizations to this model which are more physical. Okay, so with respect to what we did last time, here it will be a bit different approach. The point is that we will rescale the problem, write it in a non-dimensional setting, and then compare these coefficients that you obtained, some of them, with regards to epsilon. We did that before, but here we're doing it in a different setting. And then we will try to find the critical case and then address it. So let us write the problem. In non-dimensional form. So you have the following: x1I kappa. So it's a lot of new variables and unknowns. So x1I over Li. But this is, in engineering literature, they almost always ask you to write the problem in a non-dimensional setting. So in mathematics, we are not maybe so much used to doing this, but it's very reasonable to write it in this form. So like y2 kappa I is x2 I over epsilon Li. y3 kappa I. So I'm rescaling with respect to epsilon, and also writing it in non-dimensional form. So U kappa is U epsilon over V ref then W kappa is epsilon Li over V ref VE. The pressure is rescaled in this way. So epsilon squared Li over V ref Ni plus Ni R, the epsilon. Then you have, this will be the parameter that we will compare with respect to epsilon. So R1 epsilon I is Ca plus Cd over ni plus ni r Li squared R2 epsilon I is C0 plus CD minus CA over ni plus ni r Li squared, and n is ni over ni plus ni r. Okay, so these two will be important to look with respect to epsilon. Okay, and now what you have, well, system 1 becomes, okay, we neglect the nonlinear terms, as I mentioned, the reasons, and you can include them, but it wouldn't change much with regards to our analysis. So system 1 becomes, of course, a very nasty system, but I like to write it down, so I will. So minus Laplace y kappa u kappa minus epsilon squared. Here it's, I think, a lot has been done already with the system. It's multiplied by epsilon squared and with the respective values, constants that appear in front when you do the change of variables. So epsilon squared 2 times derivative over x1 plus 1 over epsilon gradient E kappa plus d kappa over x1 kappa E1. Okay, so this is equal to 2n. So d v3 kappa over dy2 kappa. So this is from the rotation, the first component. Okay, plus rotation y v1 minus you have these two terms, so epsilon d v3 kappa over dx1 kappa v2 plus epsilon d2 kappa over dx1 kappa v3. So this is the momentum equation. The divergence equations is, of course, much more simple. So divergence y kappa u kappa plus epsilon. So this is multiplied by epsilon. Okay. And what is important is that here in the angular momentum equation, you have this R1 epsilon. Oh yes, we also omit the I superscript, just to keep it simple. So R1 epsilon Laplace over y d kappa plus epsilon squared d squared d kappa. Okay, so this is from the Laplace. Then you have from the gradient divergence rescaling, so gradient divergence plus epsilon d over dx1 kappa okay plus epsilon. So this is all from the gradient of the divergence. So here you have gradient dv1 kappa over dx1 plus epsilon squared d squared v1 kappa Okay, you have this. I know it's nasty, but I think it's good to write it down. Have an overview. So plus 4n epsilon squared v kappa. And you basically have the same term, but with u on the, let me just check, on the right hand side. So you have this, so 2n epsilon squared du3 kappa over dy2 kappa minus du2 kappa over dy3 times e1 plus epsilon squared rotation y star kappa minus epsilon to the third du3 kappa over d. You have different scaling with, as you can see, for v kappa you have the epsilon. This is why this appears. So du3 kappa dx1 e2 plus epsilon squared. I will just check this in the paper. du2 kappa over dx1 d3. Let me just check if the coefficients are okay. Yeah, I think you have epsilon to the third now. So here you have epsilon to the third. Okay. So this is posed in the following domain. Of course, this is why I write it in this form, because this will, the value of these with respect to epsilon will play an important role, and we will discuss this in a minute. So this is formed and posed basically in omega kappa, which is x1 kappa, y star kappa. So this x1 kappa is from 0 to 1, of course, and y star, which is y2, y3, it's from b 0, 1. Okay, as I mentioned, we did not write the nonlinear terms. So the nonlinear terms, and I will denote this by 3. I don't remember if I didn't denote the original system is 1 and the boundary conditions are denoted by 2. I think I didn't. So the nonlinear terms in 3, since they do not contribute to the macroscopic model. Okay, so let me just first erase this. At least up to this point. So to simplify the notation, superscript. The superscript I, and use the following. So partial differential operators. So they are natural, and I think I wrote it a couple of times, but it's not bad maybe to just write it again. So divergence of y star v is the v2 over the y2. So dv3 over dy3, the Laplace of y star v so it's the what you can naturally expect. So the second derivative over y2 and plus the derivative over y3. Then vk is v times ek. K is 1, 2, and 3. And then gradient y v is dv over dy2 e2 as is expected, and I'll just write down the rotation. So rotation y star v is dv over dy3 e2 minus dv over dy2 e3, where y star is y2, y3. Okay, so now what we'll be talking about today is basically you have three different macroscopic models. So with regards to the comparison of R1 epsilon and R2 epsilon with respect to epsilon, more precisely with respect to the critical case will be epsilon squared. So, but if you put, we'll first consider what if it is smaller than epsilon squared or larger. So let's talk about this a bit. So it's a bit different than what Professor Poloka did. There we didn't have the rescaling and the comparison of the viscosity coefficients, but a more general setting. Just check. Okay, so I have three different macroscopic models. So in the first two cases, when you are not considering the critical case, when these two perimeters are of order epsilon squared, then you have weak coupling, and it is more or less easily solvable. In the critical case, you will have strong coupling, and this will be solved via Lax-Milgram theorem. So let's consider the first case. So our y epsilon is much smaller than the order of epsilon squared, where y is 1 and 2. Okay? So if this is the case, then from the epsilon squared term, v3 we have the following. So I have epsilon squared. So v kappa, you obtain that v kappa is exactly 1/2. So du3 kappa over dy2 kappa minus du2 kappa dy3 E1 plus the rotation of y star of u1 kappa. Okay, and you can denote this by 4. I'll write it down. So this is basically du1 kappa over dy3 kappa E2 minus du1 kappa over dy2 kappa E3. Okay, and now that you have this, you now obtain from, so this is from the angular momentum equation, the epsilon squared term, and from the momentum equation and the divergence equation, so free 1 and free 2. So this is the rescaled equations. You obtain the following system, simple system. So by epsilon to the minus first, you have the gradient of p kappa is 0, which means that p kappa is dependent just on x1, which is more or less expected. Then by 1, you have minus Laplace y kappa, u kappa plus d kappa over dx1 kappa e1. Okay, so this is equal to, on the other hand, 2n, the rotation basically of the micro rotation. So the v3 kappa dy2 kappa dv2 over dy3 e1 plus rotation of y kappa star d1 kappa. Okay, and of course the divergence of u kappa y star kappa is equal to 0. Okay. Now plugging. So I can denote this by 5. So if I plug 4 into 5, 2, I obtain the following. So you obtain the following. So 1 minus n Laplace u1 kappa minus dp over dx1 kappa is 0. This is by this is in the first component. Then you have Laplace y kappa u2 kappa plus n. So d squared u3 kappa over dy2 kappa dy3 minus the second derivative of u2 kappa dy3 kappa. So this is 0. the second component and very similar in the third component. Let's write it down. So Laplace y kappa star u3 kappa plus n so basically very similar, but u3 and u2 are replaced. So here you have u2 kappa y2 y3 minus u3 y2 kappa squared. So this is 0 in the third component. Okay. So what you have now, besides this, you can denote this by 6. You have the following boundary conditions. So the boundary conditions. So the boundary conditions read u kappa is 0 on 0, 1 times the boundary of B, and P kappa is Qi kappa for x1 equals to 1, where Qi kappa is epsilon squared Li over B ref Ni plus Ni R Qi. Okay. So you can find an explicit solution. So the solution of the system is given in the following form. So you have u kappa y star kappa. So you have q0 kappa minus qi kappa over 4 1 minus n 1 minus the absolute value of y star kappa e1. So it's more or less easily computed from this, and you have no problems. As you can see, we do not use the asymptotic expansion method here. We're just working with basically the zero-order approximation. The effect of the micropolarity is already present here. So, effect of the micropolarity through Ni R. Okay, and you also have so this P kappa of x1 kappa, just q0 kappa plus qi kappa minus q0 kappa x1 kappa. Okay, so this is where q0 kappa is epsilon squared L ref, which is basically the reference value. I'll write it down over V ref plus NR, and Q0 times Q0, where Q0 stands for the constant value. So the constant value of the the pressure at the junction point. And this reference value is basically the sum of the length of the pipe. Okay, so as you can see in this case, it's you can consider it interesting, but definitely we need to consider other cases as well. So there are some effects. You have some micropolarity here, but basically you have the classical Poiseuille solution. With regards to before the break, I'll just write down what happens in the other case in very short words. So when you take R y epsilon, which is much bigger than epsilon squared, so both of them are much bigger. So y equals 1 or 2. So this means epsilon 1 and 1 over epsilon, etc. What you then obtain is from free. I'll not write it down. You can check it in the paper. We obtain not very interesting case. So we obtain that V kappa is 0. And from the angular momentum equation, you obtain that this is 0. And from the other two equations, you obtain a Poiseuille-like solution again, which is expected. Poiseuille-like solution. So modified by the constant factor 1 minus n, which appears regularly in these expressions. Okay, so this was the rescaling and the first two cases. We will have a, 10-minute break, which is usual, 5 to 11, 5 to 11. And I will talk a bit about the most critical case and how to prove the existence and uniqueness of the corresponding solution. Okay, see you in 10 minutes.